Welcome to this lecture in the ongoing series of lectures in real analysis. We are nearing the end of the course, and today we'll be looking at the exponential function. Previous, let's say, 8 lectures were basically in preparation for this particular lecture, and finally we are here. Okay, so to construct the exponential function, we'll have to define it, but the key ingredient in construction, or rather in proving that the construction works, is this ratio test, which says that if you have a series with no term being 0, then the series converges if this lim sup is less than 1. We don't really need the second one, so let me erase it. We don't need the second part. So this series converges if, it's not an if and only if, it's just an if this happens. Okay, great. So what is the exponential function? Typically, exponential function is defined by a power series. In any, mostly I think textbooks or lectures, people what they do is they take a power series and show that, well, that converges and that's your exponential function. Its radius of convergence is infinity, so it converges everywhere and so on and so on. But to me, that doesn't seem like a very well motivated definition. I would like to start with the definition which is, at least to me, a bit more motivated. Anyway, so suppose we have a function. Before I even define the exponential function, suppose we have a function which is differentiable and it satisfies this property, very strange looking property, that the function is its own derivative. So if you differentiate this guy, you get the same guy back. So the thing that we will show first is that if this function takes the value 0 at let's say at 0, then this function is actually identically 0, meaning it takes the value 0 everywhere. Okay, so if you have a differentiable function on the real line, differentiable everywhere, which is its own derivative, and it takes the value 0 at the origin, then it is 0 everywhere. So this is what we'll prove first, and then we'll say what we mean by the exponential function. All right, so here's the proof. The proof is interesting. Okay. So by the fundamental theorem we have, by fundamental theorem of calculus, we have and I will use this notation where you introduce a dummy variable. Okay, so why can we say this? Basically, we can integrate something if it is integrable, Riemann integrable, and since f is its own different derivative, f is differentiable as many times as you want, because f is differentiable and f prime equals f, so f prime is also differentiable. In particular, f prime is continuous, and therefore this integral makes sense, and we can apply the fundamental theorem of calculus to write this. Okay, great. So we get this is equal to because f prime is equal to f. So of course we have this equality, and this is at most the integral of the absolute value. This is one of the things that we discussed earlier in the module on Riemann integration. So we have that. So thus if we write g to mean the absolute value function of f, we have that gt, which is that, is at most integral 0 to t of that guy, which is g of s ds. So we have this inequality, and let's maybe mark it because we'll use it later. Okay, just be mindful of this one. So what we will show is that G vanishes in a right neighborhood of the origin. And similarly, you'll be able to show that it also vanishes in a left neighborhood. And that part I leave as an exercise. I'll just show the right neighborhood part. Okay, so how do we do this? So let some t naught in this closed interval, 0 to half, such that the supremum of G in this region is achieved at t naught. So why can we find such a t naught? Well, G is a continuous function because the absolute value function of a continuous function is continuous. And this is a compact set. And a continuous function achieves its supremum on any compact domain. And therefore there is a t naught. There could be multiple such t naughts, but there is a t naught such that this equality holds. Okay, fine. So if this were 0, then gt naught is 0, of course, because f0 is 0 and therefore g0 is 0, and hence gt naught will be 0, which would mean that this supremum is 0, but since g is already a non-negative function, that would mean that g takes the value 0 everywhere on this closed interval, and hence what we wanted to prove, we would have proved that this yellow statement would then hold, because the right this is a right neighborhood of 0. All right. So if t naught were equal to 0, then we are done. So we may assume that t naught is not equal to 0. Okay. So then gt naught is less than equal to where is this coming from? This is coming from the orange thing. Which is less than equal to t naught gt naught. Why is that? Because each of this is less than equal to gt naught. Right? In this entire interval, the supremum is achieved at t naught, so gs will be at most g naught in this, which is of course a subset of that guy. So in this region, since the integrand is dominated by gt naught, the integral is also dominated that way. All right. So basically what I've done is this. Let me just do one step. So this is at most integral 0 to t naught gt naught. That's what I did actually. That, yes, which is equal to t naught gt naught. And this is at most half gt naught, because this guy is at most half. So what do we see? We see gt naught is at most half gt naught, and this is already the case. Let me write that also. So if you just look at this, we see that gt naught is 0. And therefore, the yellow statement holds. Therefore, the yellow claim holds. Okay. So we have shown that G vanishes on a right neighborhood of 0, and hence, similarly one can show that the conclusion is that thus G vanishes on a neighborhood of 0. Because you can similarly show the left neighborhood thing. Alright. So now what we want to show is that G vanishes everywhere, because we want to show that F vanishes everywhere. Okay. So this is how one can do it. Let S be this set, T which is positive, G or F vanishes in 0 to T, or vanishes everywhere in 0 to T. As we just saw that S has positive numbers. Alright, so let S naught equal supremum of S, and if S naught is infinite, then F vanishes everywhere on the non-negative real line. And if not, if S naught is finite, then repeat the above argument. Argument on the previous page. Repeat the above argument to show that F vanishes on a right or on a neighborhood of S naught. This would contradict that supremum of S is S naught. So let me explain this last line. So if this is the origin, this is S naught, by definition F vanishes everywhere here. By continuity of F will vanish in fact everywhere here in this closed interval. And now just like we argued for the origin, we can argue for this point and show that there is actually a neighborhood of this guy where F vanishes, which would mean that F vanishes actually everywhere here, which would in turn imply that the supremum of S is at the very least this number, and contradicting the supremum of S is equal to S naught. So that's how that argument will go. So in conclusion, S naught will have to be infinite, and hence we have shown that this set is unbounded, and which implies F vanishes everywhere on the non-negative real line. And similarly, you can show that the F vanishes everywhere on this side, on the negative real line. And hence F vanishes everywhere, and that's it. And we are done. I'm not writing those details, but that's a proper argument. So here the details that I have skipped, you should take them as an exercise and write down your own proof. But the main meat of the argument is this. All right, wonderful. So this has a simple corollary, and after this I'll define the exponential function. So the corollary is this, that suppose you have a function f which is like this, meaning its derivative is itself, and it takes the value 1 at the origin. Then there is at most one such function. You cannot have two different functions satisfying both of these properties. And if you are familiar with differential equations, which I do not assume you are, but if you are, then you see that this is an initial condition and this is a differential equation, and a general theorem about differential equation says that any differential equation degree 1 with one initial condition has a unique solution, unique maximal solution. Anyway, it doesn't matter. So let's see why, because this is very simple. This is immediate from the previous one. So if f1 and f2 satisfy f1 prime equals f1, f2 prime equals f2, and f1 0 equals 1, f2 0 equals 1, then set f as f1 minus f2. Thus f prime equals f1 prime minus f2 prime, which is f1 minus f2, which is f. So f prime equals f, and f prime 0 is f1 prime 0 minus f2 prime 0 equals 1 minus 1, which is 0. So this just means that f equals f prime and f0 equals 0, which by the previous lemma implies that f is identically 0, which implies that f1 equals f2. So if we had two functions satisfying both these conditions, two functions from R to R satisfying both these conditions, then they have to be equal, and therefore there is at most one such function. And now we can define the exponential function. So this corollary is proven, and now we define so the exponential function, a function, or rather now we can say the exponential function, exponential function is defined as a differentiable function f from R to R such that it is its own derivative and it takes the value 1 at the origin. As we have shown, there is only one such function, so it has this definite article. This is justified. However, just because we can define something doesn't mean that thing exists. I mean, for instance, I could write the exponential function is defined as a differentiable function with this, and I could write another, f1, f0 is also 2. Now, of course, there is no such function. There is no function which satisfies both these conditions simultaneously. So just because I can define something doesn't mean it exists, so we have to show that it exists, and we will show this by construction. We will construct a function which satisfies these properties, and that will be it. Now, to construct it, we need, after all, we have to have some inspiration, and the inspiration comes from Taylor's theorem. So what we have is, let's say f is a function. This is an informal discussion. So suppose f is a function with f prime equals f and f0 equals 1. Then what is f prime of 0? Well, f prime of 0 is f0, and therefore that is also 1. What is f double prime of 0? So if you look at this, it says that f prime is f, and therefore f double prime is f prime, meaning the double derivative of f is same as single derivative of f. I just differentiated this guy both sides. So this is equal to f prime of 1, f prime of 0, and f prime of 0 is 1. So this is also 1. Basically the point is that all the derivatives, you take the kth derivative, and at 0 it is 1. Now what does Taylor's theorem say? Taylor's theorem says that f of 0 plus h, I'm writing it in this fashion, basically this is f of h. This is, actually I don't really remember, but this is m is equal to 0 to k, what is that? H to the power k, 1 upon k factorial, maybe not like this, so it is f kth derivative at 0 divided by k factorial, h to the power k, plus some remainder term. Remainder term I will not write. So this is the polynomial term. I hope I have not made a mistake. Yeah, this is the polynomial term. So basically, since all those derivatives are 1, this is equal to some remainder term, which of course depends on h and whatnot. Okay. So f of h looks like this, but there is no reason to stop at any particular case. So our guess is that f of h should be, or let me just say f of x should be equal to summation m equals 0 to infinity 1 upon m factorial x to the power m. So this is our guess. Now it is not clear that this is in fact a genuine function. On the right hand side, this series may not converge at all, or God knows where it converges, what is its radius of convergence. So that's the next thing. If this converges everywhere, then we do have a function which at least is a good candidate to satisfy these conditions. It certainly satisfies this condition, right? Because at x at m equals 0, this is a 1 and this is also a 1, so it satisfies this condition. We have to check that it also satisfies that. So let's calculate the radius of convergence of this guy and proceed. All right, so here is the formalism. So lemma, the radius of convergence of this series x to the n upon n factorial is infinite. So we'll use the ratio test. We have the lim sup. So none of these coefficients are 0, and therefore we can apply the ratio test. And the ratio test says that lim sup n going to infinity, or forget about any power series. This is just fix some real number x. This is an infinite series. I'll just show that it converges. If x is 0, then nothing to be done. If x is non-zero, then none of these terms are 0, and I can apply the ratio test. So this lim sup I have to calculate x, the n plus 1th term, and the nth term, which is, if you just do some algebra, it is equal to that, which is equal to 0 in fact. This lim sup is 0 because this is 1 upon n plus 1. This thing is 1 upon n plus 1. So that is 0, and which is of course less than 1. And therefore this converges. So for each non-zero x, this thing converges. For x equals to 0, this is obviously convergent. So this converges everywhere, hence the radius of convergence of that power series. If you think of this as a power series, then the radius of convergence is infinite. And we have proven the lemma. All right. So Now we have a convergent power series, and we know that we can differentiate power series are differentiable in their radius of convergence, and the derivative can be just taken term by term. So if f is defined as, now it is a genuine definition, f of x equals, by the previous lemma this is a genuine definition, because the power series converges everywhere, therefore it is legitimate to define it. And we have the derivative of this guy is just obtained by differentiating term by term. So this is n equals 1 to infinity 1 upon n factorial n x to the power n minus 1, which is equal to x to the power n minus 1, which is nothing but n equals 0 to infinity 1 upon n factorial x to the n, which is f of x. So it does satisfy the condition that f prime equals f, and f0 is clearly equal to 1. This is obviously true, and hence we have indeed found a function which satisfies both those things. One is this, and the other is that f prime equals f. We have shown that there is only one such function, and this is called the exponential function. Lastly, I'll just end with notation. Forget about this. So notation for we have e to the x. Instead of writing this all power, this long power series, we just write e to the x. So this is the notation for that thing. And yeah, now you can we will say more about what is this e thing, but right now this is just a notation. We will see that e is actually a number, that there is a number which if you exponentiate you get that. We'll come to that later, but right now this is just a notation. So alright, this is all that I wanted to say. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.